what if the universe's speed limit isn't as absolute as we were taught? For over a century, physics has insisted on one rule above all others. Nothing moves faster than light. Not information, not matter, not gravity. It is the ultimate boundary of reality itself. But that certainty is cracking. Physicists have now identified 5 mathematically consistent ways to travel faster than light without breaking the laws of physics. These are not sci-fi fantasies. They are peer-reviewed frameworks, derived from Einstein's own equations, and one of them may be buildable. This is the terrifying part. If even one of these pathways is real, the universe instantly becomes reachable. For light years shrink 2 weeks. The Milky Way becomes crossable within a millennium. Every distant star stops being scenery and becomes a destination. NASA has already studied the most famous of these ideas, the Alcubierre warp drive, not as fiction, as engineering. So what changed? Why does Einstein's speed limit suddenly have loopholes? And if faster than light travel is possible, what else have we been wrong about? Because once that door opens, the universe is no longer far away. Let's begin. Part 1. The foundation of faster than light travel and historical barriers. The opening challenge and fundamental claim. What if everything you've been told about the universe's ultimate speed limit is about to change? For more than a century, physicists have hammered one message into our collective understanding. Nothing in this universe can travel faster than light. 186,282 miles per second. That's the cosmic barrier, the unbreakable law, the final word on how fast anything can move through space. But here's where things get interesting. Scientists have now identified 5 distinct theoretical pathways that could allow us to travel 100 times faster than light. Not just theoretical daydreams scribbled on napkins, but rigorous mathematical frameworks published in peer-reviewed journals by respected physicists at major research institutions. The equations work, the math checks out, and one of these methods might actually be buildable within the next 5 centuries. Now, before you start packing for Alpha Centauri, let me be crystal clear about something. These theories come with challenges that would make climbing Mount Everest look like a casual stroll through your neighborhood park. We're talking about energy requirements equivalent to converting the entire mass of Jupiter into pure power. We're discussing materials that might exist only in the realm of theoretical physics. We're facing engineering problems that humanity won't solve for generations. But here's what makes this moment in scientific history absolutely revolutionary. For the first time ever, physicists can show you the specific mathematical pathways that make faster than light travel possible, without breaking the fundamental laws of physics. Think about what that means for a second. Throughout human history, we've looked up at the stars and understood them as beautiful, distant objects we could observe but never touch. The nearest star system to Earth sits more than 4 light-years away, meaning even if we somehow built a spacecraft capable of traveling at 99% of light speed, the journey would still take over for years. And that's just our closest stellar neighbor, the center of our Milky Way galaxy, 26,000 light-years distant. At conventional speeds, even hypothetical near-light-speed vessels would require tens of thousands of years to reach it. The universe has always been, in practical terms, completely and totally unreachable. But one of these 5 theories changes that calculation entirely. It's called the Alcubierre warp drive, named after the physicist who first proposed it in 1994. And unlike the other 4 theoretical approaches we'll discuss, this one stands out for a crucial reason. Scientists have already calculated specific designs, identified the physics principles involved, and mapped out potential technological pathways. When researchers at NASA, yes, NASA, started seriously investigating this concept in 2012, they weren't just entertaining science fiction fantasies. They were working through genuine engineering challenges. The implications of this research extend far beyond simple space travel. If humanity can eventually build a functioning warp drive capable of traveling 100 times the speed of light, we could reach Proxima Centauri in about 2 weeks, instead of 4.2 years. We could cross the entire Milky Way galaxy, 100,000 light-years from edge to edge, in roughly 1,000 years. Suddenly, the galaxy transforms from an untouchable cosmic display into humanity's potential backyard. Every exoplanet we've discovered through our telescopes becomes a destination we could theoretically visit. Every mysterious signal from deep space becomes an address we could actually travel to investigate. So how did we get from Einstein's supposedly ironclad speed limit to NASA scientists calculating warp drive specifications? What changed in our understanding of physics that opened this door? And why are some of the world's most brilliant minds dedicating their careers to solving problems that might not be resolved until the 26th century? Those are the questions we're going to explore together. And I promise you, the answers will fundamentally change how you think about humanity's future among the stars. Einstein's framework and the problem it created. To understand how we might break the light-speed barrier, we first need to understand why that barrier exists in the first place. And that story begins in 1905, when a 26-year-old patent clerk in Switzerland published a paper that would completely revolutionize physics. Albert Einstein's special theory of relativity didn't just tweak existing scientific understanding. It demolished the fundamental assumptions humans had made about space and time for thousands of years. Before Einstein, everyone assumed space was space and time was time. They were separate, independent, absolute. Newton's laws described a universe where time ticked forward at the same rate everywhere, and space provided a fixed stage where events unfolded. Einstein proved that entire worldview was wrong. Space and time aren't separate entities. They're interwoven into a single four-dimensional fabric called space-time. And here's the part that changed everything. The speed of light isn't just another velocity that happens to be really fast. It's woven into the fundamental structure of space-time itself. Light travels at exactly 186,282 miles per second because that's the conversion rate between space and time built into the universe's basic architecture. Think of it this way. Imagine space-time as a cosmic highway with absolute traffic laws enforced by the laws of physics themselves. Light speed isn't just the posted speed limit. It's the actual maximum speed the highway can physically support. And here's where things get brutal for anyone dreaming of interstellar travel. As you accelerate toward that speed limit, the universe throws up 3 increasingly impossible obstacles. First, your mass increases. Not your weight, your actual mass. The faster you go, the more massive you become. At 90% of light speed, your mass has increased by about 2.3 times. At 99%, you're about 7 times more massive. At 99.9%, you're over 22 times more massive than when you started. This isn't some optical illusion or measurement error. Your actual inertia, your resistance to further acceleration, genuinely increases as you approach light speed. Second, time dilation kicks in. From your perspective inside a spacecraft approaching light speed, time passes normally, but relative to the universe outside, your clock runs slower and slower. At 99.9% of light speed, for every year that passes on your ship, 22 years pass back on Earth. You could take what feels like a 5-year journey and return home to find a century has elapsed. This isn't science fiction speculation. We've measured time dilation with atomic clocks on aircraft. It's real, it's measurable, and it gets more extreme as you approach light speed. Third, and this is the killer, the energy required to keep accelerating grows exponentially. Because your mass keeps increasing, you need more and more energy to produce the same amount of acceleration. By the time you reach 99.99% of light speed, you'd need more energy than contained in most solar systems just to accelerate a tiny bit faster, and to actually reach 100% of light speed, the energy requirement becomes infinite. Not just really big, actually mathematically infinite. This is why Einstein's theory seemed to close the door on interstellar travel permanently. Any object with mass faces an insurmountable mathematical wall at light speed. You can get closer and closer, but you can never quite reach it, and you definitely can't exceed it. For 90 years, this conclusion stood as physics' final word on the subject. The universe had spoken. Faster than light travel wasn't just technologically impossible, it was fundamentally, mathematically, physically impossible according to the laws that govern reality itself. Physicists explored every conceivable loophole. Maybe antimatter could help. Nope, same energy problems. Maybe we could somehow reduce an object's mass. Can't be done without destroying the object. Maybe there's something special about photons, particles of light that do travel at light speed. Yes, but they have zero rest mass, which is why they can do it. Anything with mass cannot. Generation after generation of scientists reached the same conclusion. If humanity wanted to explore the stars, we'd have to accept that interstellar journeys would take centuries or millennia. We'd need generation ships, vessels large enough to sustain populations across hundreds or thousands of years. We'd need to either extend human lifespans dramatically or accept that the people who left Earth would never see the destination. Nor would their children or their children's children. The stars were there, tantalizingly visible in our night sky, but forever out of reach within any reasonable human time frame. But here's what nobody fully appreciated at the time. Einstein's equations didn't just describe one rigid, inflexible universe. They described a universe far stranger and more flexible than anyone imagined. And in 1994, a young physicist was about to figure out how to exploit that flexibility. The 1994 paradigm shift. Miguel Alcubierre wasn't trying to revolutionize physics when he started thinking about warp drives. He was a graduate student at the University of Wales, working on his doctorate in theoretical physics. Like many physics students, he enjoyed science fiction, particularly Star Trek, and like many physics students who watch Star Trek, he found the warp drive concept deeply frustrating. Because the warp drive, as shown on television, violates every known law of physics. The Enterprise just turns on its engines and accelerates to several times light speed. No infinite energy problem. No time dilation. No increasing mass. The show just hand waves away all of Einstein's restrictions with some fictional technology and moves on with the story. Most physicists watch that and think, well, that's impossible. Time to suspend disbelief and enjoy the show. But Alcubierre asked himself a different question. He didn't ask, how can we make the Star Trek version work? Instead, he asked something far more profound. Is there any way, within the actual laws of physics, as we understand them, to achieve effective faster-than-light travel? Notice that careful phrasing. Effective faster-than-light travel. Not necessarily moving faster than light, but achieving the same practical result. Getting from point A to point B faster than light could make the journey, and that question led him to re-examine Einstein's equations from a completely new angle. Einstein said you can't accelerate through space faster than light. That restriction is absolute and unbreakable. But here's the thing, and this is crucial. Einstein never said space itself couldn't move faster than light. Let me explain what that means. The universe is currently expanding. Distant galaxies are moving away from us, and the farther away they are, the faster they're receding. The most distant observable galaxies are receding from us faster than the speed of light. Not because they're moving through space faster than light, but because the space between us and them is expanding. And that expansion doesn't violate relativity, because the galaxies themselves aren't moving through space at that speed. Space itself is growing, carrying the galaxies along with it. This distinction might sound like semantic hair-splitting, but it's actually the key to everything. Einstein's speed limit applies to objects moving through space. It doesn't necessarily apply to space itself. Alcubierre realized you could exploit this loophole. Here's the idea. What if you could create a bubble of space around your spacecraft? And what if you could compress the space in front of that bubble while expanding the space behind it? Your ship wouldn't move through space at all. It would sit stationary inside its bubble. But the bubble itself, carried by a wave of contracting and expanding space, could move at any speed, 10 times light speed, 100 times, 1,000 times. Theoretically, there might be no limit at all. Think of it like those moving walkways you see at airports. You stand still on the walkway, not moving relative to the surface under your feet, but the walkway itself moves, carrying you forward. From your perspective, you're stationary. From an outside observer's perspective, you're moving. Now imagine that walkway could move at 100 miles per hour, or 1,000, or 100 times the speed of light. You're still not moving relative to the walkway, so you don't experience any acceleration. You don't approach light speed from your frame of reference. You're just standing still while the thing carrying you moves incredibly fast. This was Alcubierre's brilliant insight. Create a warp bubble around your ship. Make the bubble move by warping space in front and behind. The ship itself never accelerates, never approaches light speed, never faces any of Einstein's restrictions. But the bubble can travel faster than light because it's not moving through space. It's moving with space. Alcubierre sat down and worked through the mathematics. He needed to find a solution to Einstein's field equations, the mathematical heart of general relativity that would create exactly this kind of space-time warping. And incredibly, astonishingly, the math worked. He found a valid solution. The Alcubierre metric, as it's now called, describes a configuration of space-time where a bubble can move faster than light without violating any physical laws. When his paper was published in 1994, the physics community was stunned. For 90 years, everyone had assumed faster-than-light travel was fundamentally impossible. Now here was a young graduate student showing that Einstein's own equations allowed for it. The reactions ranged from excitement to skepticism to disbelief. Some physicists immediately started looking for loopholes or errors in the math. Others began exploring the implications and looking for ways to refine the concept. But nobody could deny the central point. Alcubierre had found a legitimate, mathematically valid solution to Einstein's equations that permitted effective faster-than-light travel. The door everyone thought was permanently sealed had been opened, at least a crack. And once physicists started looking through that crack, they found not just one possible pathway to faster-than-light travel, but several. 5 theoretical pathways to breaking the light barrier. Once Alcubierre demonstrated that Einstein's equations didn't completely prohibit faster-than-light travel, physicists began exploring other potential loopholes in our understanding of physics, and they found 4 additional theoretical frameworks that might under certain conditions, allow for effective faster-than-light travel or communication. Let me walk you through each one, because understanding the full landscape of possibilities helps clarify why the Alcubierre warp drive stands out as the most promising option. Theory 1. The Alcubierre warp drive. We've already introduced this concept, but let's clarify exactly what makes it special. The warp drive doesn't move your spacecraft through space at all. Instead, it creates a bubble of normal space-time around your ship. In front of the bubble, space contracts and compresses. Behind the bubble, space expands and stretches. This creates a wave in space-time itself that carries your bubble forward. From inside the bubble, you experience normal physics, normal time, normal gravity. You could walk around your ship, make coffee, read a book, but from outside the bubble, you're crossing interstellar distances at speeds that would normally require centuries. The beauty of this approach is that your ship never actually accelerates, so Einstein's restrictions never apply. The catch: you need exotic matter with negative energy to create and maintain the bubble. More on that later. Theory 2. Traversable wormholes. Einstein's equations actually predict that space-time could contain shortcuts. Imagine folding a piece of paper so two distant points touch, then punching a hole through both layers. That hole represents a wormhole, a tunnel through space-time that connects to locations that would normally be separated by vast distances. Travel through the wormhole, and you could cross from one side of the galaxy to the other in seconds or minutes, regardless of how many light years separate those locations in normal space. Here's the incredible part: you wouldn't even be traveling faster than light. You'd be traveling at normal speeds through a shortcut that makes the journey shorter. The catch: natural wormholes, if they exist at all, would be microscopic and incredibly unstable. They'd collapse almost instantly. To hold a wormhole open long enough to travel through, you'd need, wait for it, exotic matter with negative energy. Same problem as the warp drive. And even if you could stabilize a wormhole, you'd first need to physically travel to the location where you want the other end to be, which defeats the purpose unless you're setting up a permanent transit network. Theory 3. Quantum entanglement. This is where things get genuinely weird. When two particles become quantum mechanically entangled, they remain connected regardless of distance. Measure the state of one particle, and you instantly know the state of the other, even if they're on opposite sides of the universe. Einstein called this spooky action at a distance because he found it philosophically disturbing, but it's absolutely real. We've demonstrated quantum entanglement countless times in laboratories. The catch: you can't use entanglement to send information faster than light, at least not with our current understanding. Imagine you have two magical coins that always land on opposite sides. Flip one coin and it lands on heads. The other coin instantly becomes tails. No matter how far apart they are. Sounds useful, right? Except you can't control which side your coin lands on, so you can't use it to transmit a message. The correlation is instantaneous, but information still can't travel faster than light. However, some physicists are exploring whether quantum entanglement could enable something called quantum teleportation, where the quantum state of a particle could be transferred across vast distances. This research is extremely speculative and faces enormous theoretical and practical obstacles, but the fundamental weirdness of quantum mechanics means we can't completely rule it out. Theory 4. Tachyons. These are hypothetical particles that always travel faster than light. While normal particles can never reach or exceed light speed, tachyons can never slow down to light speed. For them, light speed is the lower limit, not the upper limit. Even weirder, Tachyons would have bizarre properties. As they lose energy, they speed up. To slow a tachyon down would require adding energy. The catch: we've never detected a tachyon, not once, and some physicists argue that tachyons would create causality problems, potentially allowing information to travel backward in time, which could generate logical paradoxes. Some versions of string theory predict tachyons might exist under certain conditions, but they remain purely hypothetical. If they do exist and we could somehow harness them, they might enable faster-than-light communication or even travel. But that's a very big if. Theory 5. Modified physics at extreme scales. This is less a specific theory and more a category of possibilities. Some physicists think Einstein's general relativity might not be the final word. At extremely high energies, or in certain quantum conditions, the rules might change. Maybe the speed of light isn't actually absolute. Maybe at scales we haven't yet explored, space-time behaves differently. Some quantum gravity theories suggest that at energies approaching the Planck scale, space-time might become discrete rather than continuous, which could potentially modify how light speed functions. The catch: this is highly speculative. We have no experimental evidence that physics changes in ways that would permit faster-than-light travel, and the energy scales where such modifications might occur are so extreme that we can't currently test these ideas. This category represents the possibility that we simply don't understand the universe well enough yet, and future discoveries might reveal new pathways. So there you have it. 5 different theoretical frameworks that could potentially allow faster-than-light travel or communication. But here's why we're going to focus on the Alcubierre warp drive for the rest of this journey. Of these 5 approaches, only the warp drive is engineerable in any meaningful sense. Only the warp drive allows scientists to calculate specific energy requirements, design specific spacecraft configurations, and identify specific technological milestones we'd need to achieve. The others are either pure speculation, or they face the same fundamental obstacles as the warp drive, but without the same level of detailed theoretical work. When NASA scientists decided to seriously investigate faster-than-light propulsion, they didn't study quantum entanglement or tachyons. They studied the Alcubierre warp drive. When physicists publish papers exploring how we might actually build a faster-than-light spacecraft within the next few centuries, they're working on warp drive designs. And when we talk about the possibility, however remote, of humanity becoming an interstellar civilization within the next 500 to 1,000 years, the warp drive is the technology that makes that timeline conceivable. Why the Alcubierre warp drive stands out. So what makes the warp drive special compared to these other theories? Why has it captured so much serious scientific attention? The answer comes down to 3 crucial factors: mathematical rigor, engineering specificity, and progressive refinement. First, mathematical rigor. The Alcubierre metric isn't some vague hand-wavy concept. It's a precise solution to Einstein's field equations, the same equations that describe black holes, gravitational waves, and the expansion of the universe itself. When Alcubierre published his paper, he showed his work. Other physicists could check his math, verify his calculations, and confirm that yes, this configuration of space-time is mathematically allowed by general relativity. That's fundamentally different from saying maybe quantum mechanics allows faster-than-light travel somehow. The warp drive is built on solid mathematical foundations that we can analyze, critique, and refine. Second, engineering specificity. Scientists can calculate exactly how much energy a warp drive would require. They can design the shape of the warp bubble. They can model how the space-time distortion would need to be generated and maintained. They can identify specific technical challenges: negative energy generation, precise field control, power storage and management. When you read papers about warp drive, you're reading engineering studies, not philosophical speculation. The researchers are asking practical questions. How do we create the necessary field geometry? How do we navigate while inside a warp bubble? How do we start and stop the warp field safely? These are solvable problems, even if the solutions are centuries away. Third, progressive refinement. Since Alcubierre's original paper in '94, dozens of physicists have published refinements and improvements. In '99, Van den Broek showed how to modify the bubble geometry to reduce energy requirements by a factor of 1,000. In 2012, Harold White at NASA found further optimizations that reduced the energy needs by another factor of billions. This is what real scientific progress looks like. Each generation of researchers builds on the previous work, finding more efficient designs, identifying new possibilities, and gradually making the seemingly impossible merely incredibly difficult. Compare that to tachyons, where we have the same basic theoretical framework we had decades ago with no experimental evidence and no clear path to testing the theory. Or quantum entanglement, where we understand the phenomenon but can't identify any mechanism for using it to exceed light speed. The warp drive is different. It's a living field of research with measurable progress over time. And here's what really matters. The problems standing between us and a functioning warp drive are engineering problems, not physics problems. Physics says the warp drive is possible. The equations work. The concept is sound. What we don't have yet is the technology to generate negative energy in sufficient quantities to shape space-time with the required precision, or to generate and store the necessary power. Those are monumental challenges, but they're not fundamental impossibilities. They're problems that future technology might solve. Think about what that means. For the first time in human history, we can look at the stars and say with mathematical certainty that reaching them within human timeframes is theoretically possible. Not guaranteed, not easy, not soon, but possible. That's a profound shift in perspective. For thousands of years, the stars were beautiful but unreachable. For the last century, physics seemed to prove they'd remain unreachable forever. Now, for perhaps the next several centuries, we'll be working to transform theoretically possible into technologically achievable. Some physicists estimate we might see the first experimental warp field, a tiny bubble of warped space maintained for a fraction of a second, within 200 to 300 years. A functional spacecraft capable of faster-than-light travel. Maybe 500 years from now. That timeline depends on continuous technological progress, stable civilization, and substantial investment in advanced physics research. But it's not science fiction anymore. It's a long-term engineering project. And that brings us to the question you're probably asking right now. Okay, so the math works. The concept is sound. But how would you actually build one of these things? What are the specific technical challenges? What technologies would need to be invented? And why do some scientists think the first warp drive could be constructed within the next 5 centuries? Those are the questions we'll explore in the next part of our journey. Because understanding the engineering challenges is just as important as understanding the physics. And some of those challenges are far more fascinating and far more solvable than you might think. Part 2. Alcubierre Warp Drive, Discovery and Core Mechanics, the birth of a revolutionary idea. Miguel Alcubierre wasn't some isolated genius working in a secret laboratory when he developed his groundbreaking theory. He was a 28-year-old doctoral student in 1994, sitting in an office at the University of Wales, Cardiff, working on problems related to numerical relativity. His dissertation focused on complex mathematical techniques for solving Einstein's equations using computers. Standard theoretical physics work. Nothing that would suggest he was about to change humanity's understanding of interstellar travel forever. But Alcubierre had a habit that many physicists share. He loved science fiction, particularly Star Trek, and one evening, while watching an episode featuring the Enterprise jumping to warp speed, something clicked in his mind. Not the usual physicist's irritation at fictional technology that violates known physics. Instead, he found himself asking a genuinely profound question. Could there be any way, within actual physics, to achieve what Star Trek's warp drive accomplishes? Most physicists would dismiss this as a fun thought experiment and move on. After all, generations of brilliant minds had already concluded that faster-than-light travel was impossible. Einstein's special relativity proved it mathematically. The cosmic speed limit of light was absolute. Case closed. But Alcubierre approached the problem from a different angle entirely. He didn't ask, how can we make a ship go faster than light? Instead, he asked, how can we make a ship arrive at a distant location faster than light could make that journey? That subtle distinction changed everything. Einstein's restrictions apply specifically to objects moving through space. As you accelerate through space toward light speed, your mass increases, time dilates, and the energy requirement approaches infinity. These effects make reaching or exceeding light speed mathematically impossible for any object with mass. But here's the loophole that Alcubierre recognized. Einstein never said space itself couldn't move faster than light. Think about cosmic expansion. Right now, distant galaxies are receding from us faster than light speed, not because they're rocketing through space at incredible velocities, but because the space between us and them is expanding. The galaxies themselves remain relatively stationary in their local reference frames. Space is growing, carrying them along, and this expansion doesn't violate relativity because the galaxies aren't moving through space faster than light. Space itself is changing, and Einstein's speed limit doesn't apply to the expansion or contraction of space itself. Alcubierre realized you could potentially exploit this distinction. What if you could create a localized region of space-time that contracts in front of a spacecraft and expands behind it? The ship wouldn't move through space at all. It would remain stationary within a bubble of normal space-time, but that bubble, carried by a wave of contracting and expanding space around it, could move at any speed without violating Einstein's equations. The analogy he liked to use was a moving walkway at an airport. Imagine you're standing still on one of those automated walkways. From your perspective, you're not moving. Your feet are planted on the surface beneath you. You're stationary. But from the perspective of someone standing off the walkway, you're moving forward. The walkway is carrying you. Now imagine that walkway could move at 100 miles per hour, or 1,000, or even 100 times the speed of light. You're still not moving relative to the walkway surface, so you don't experience acceleration. You don't face Einstein's restrictions, but you're covering vast distances incredibly quickly because the thing carrying you is moving. This is the core insight behind the Alcubierre warp drive. Create a bubble of space-time around your spacecraft. Compress space in front of the bubble. Expand space behind it. The ship sits in the middle, in a region of flat, normal space-time, experiencing regular physics. But the bubble itself moves through the universe at faster-than-light speeds, carrying the ship along for the ride. Alcubierre sat down with Einstein's field equations and started working through the mathematics. Could you actually construct a space-time geometry that would create this kind of bubble? Could you write down a metric, a mathematical description of how space-time curves that would produce the desired effect? And crucially, would this metric be a valid solution to Einstein's equations? Or would it require violating some fundamental physical law? The mathematics was complex. Alcubierre had to carefully specify how space-time would be curved at every point around the bubble. Too much curvature in the wrong place, and the bubble wouldn't move. Too little, and you'd need infinite energy. The geometry had to be precisely balanced. But after weeks of calculations, checking and rechecking his work, Alcubierre found something remarkable. The math worked. He had discovered a valid solution to Einstein's field equations that described exactly the kind of space-time bubble he'd imagined. The Alcubierre metric, as it's now called, describes a region of space-time that can move faster than light without violating general relativity. When he submitted his paper for publication, the response from the physics community was immediate and intense. Some researchers were excited, recognizing the elegance of the solution. Others were skeptical, searching for errors or hidden problems. Still others were simply shocked that such a solution existed at all. But nobody could find a fundamental flaw. The mathematics was sound. The solution was valid. Alcubierre had proven that Einstein's equations, the same equations that seemed to forbid faster-than-light travel, actually allow for a mechanism that achieves the same practical result. The door that everyone thought was permanently sealed had been opened, and the scientific world would never look at interstellar travel the same way again, understanding the warp drive mechanism. So how does the Alcubierre warp drive actually work? Let's break down the physics in a way that makes sense without getting lost in complex mathematics. Because once you understand the mechanism, you'll see why this concept is so brilliant and why it avoids all of Einstein's restrictions on faster-than-light travel. Start by imagining space-time as a flexible rubber sheet. This is the classic analogy physicists use to explain gravity, and it works perfectly here too. Now, picture your spacecraft sitting on this rubber sheet. In normal circumstances, the sheet is flat around your ship. That represents normal, undistorted space-time where Einstein's usual rules apply. But now we're going to do something unusual. We're going to deform this rubber sheet in a very specific way. In front of your spacecraft, we're going to compress the sheet, squeeze it together. Imagine grabbing the rubber and pushing it into a tighter, more compressed configuration. This represents space contracting. The distance between points decreases. If you had two markers on the sheet a foot apart, after compression they might only be 6 inches apart, even though neither marker moved. Behind your spacecraft, we're going to do the opposite. We're going to stretch the rubber sheet, pull it apart, expand it. Now those two markers that were a foot apart might be 2 feet apart, even though, again, neither marker actually moved. The space between them expanded. Your spacecraft sits in the middle of these two regions in what's called the warp bubble. Inside this bubble, space-time remains completely flat and normal. You could walk around your ship, conduct experiments, measure time with clocks, and everything would behave exactly as it does here on Earth. You wouldn't feel any strange forces. Time wouldn't behave weirdly. Gravity would be normal. The interior of the bubble is a safe, comfortable region of ordinary physics. But the boundary of the bubble, where normal space-time transitions into the compressed region in front and the expanded region behind, is where the magic happens. This boundary creates what physicists call a warp field. The compressed space ahead of the bubble and the expanded space behind it generate a wave in space-time itself, and this wave propagates forward, carrying the bubble along with it. Here's the crucial part. that makes this different from normal propulsion. Your spacecraft isn't pushing against anything. It's not expelling reaction mass. It's not firing rockets. The ship itself isn't moving at all relative to the spacetime inside the bubble. If you were sitting in the pilot's seat, you wouldn't feel acceleration. You wouldn't be pressed back into your seat. From your perspective, you'd be completely stationary. But from the perspective of the universe outside your bubble, you'd be moving. Fast, potentially much faster than light. Because while the space inside your bubble isn't moving, the bubble itself is being carried forward by the wave of contracting and expanding spacetime around it. Think back to that airport walkway analogy. You're standing still on the walkway, so you don't feel like you're moving, but the walkway is moving, carrying you forward. Someone standing off to the side watches you glide past. In the warp drive, the bubble is the walkway, and the wave of space-time distortion is what's moving the walkway forward. This mechanism sidesteps all three of Einstein's restrictions on faster-than-light travel. First, there's no mass increase because your ship isn't accelerating. From the ship's reference frame, it remains stationary. Mass only increases when you accelerate through space, and that's not happening here. Second, there's no time dilation. Time dilation occurs when you're moving at high velocities relative to another reference frame, but inside the bubble, you're not moving relative to your local space-time. So time progresses normally. You could take a journey across the galaxy, and when you return home, you'd have aged exactly as much as the clocks on your ship indicate. No time travel effects, no relativistic complications, and third, regarding energy requirements, well, this is where things get complicated in a different way. You're not fighting Einstein's exponentially increasing energy curve because you're never approaching light speed from your own reference frame. The energy requirements for a warp drive are enormous, make no mistake, but they're not infinite. They don't increase exponentially as you go faster. In principle, you could set the bubble to move at 10 times light speed, 100 times, or even 1,000 times. And while each increase requires more energy, it scales linearly rather than exponentially. The warp field itself requires precise geometric configuration. Think of it like a wave at the beach. If you've ever watched surfers, you know they need to position themselves at just the right spot on the wave. Too far forward, and they lose the wave. Too far back, and the wave passes them by. The warp bubble is similar. The space-time curvature needs to be strongest at the forward and rear edges of the bubble and weakest in the middle where your ship sits. The transition from normal space to warped space needs to be smooth enough that you don't need absurd amounts of energy, but sharp enough that the wave actually propagates forward. Harold White, the NASA physicist we mentioned earlier, calculated that the optimal shape for a warp bubble looks somewhat like an American football, elongated, with the strongest space-time distortion at the front and back, and a relatively flat region in the middle where the spacecraft would be located. This shape minimizes the energy requirements while maximizing the forward motion of the bubble. The warp field has to be maintained continuously. You can't just create it once and coast. As your bubble moves through space, it encounters slight variations in the space-time around it. A distant star here, a gas cloud there. Even the cosmic microwave background radiation affects the local geometry of space slightly. Your warp field needs to constantly adjust, compensating for these perturbations, maintaining the precise geometry required to keep the bubble moving smoothly and at the desired velocity. This means you'd need incredibly sophisticated control systems. We're talking about sensors that can detect minute changes in space-time, curvature, and adjust the warp field thousands or millions of times per second. The James Webb Space Telescope adjusts its mirror segments with nanometer precision to maintain perfect focus. A warp drive would need to adjust space-time itself with even greater precision. Challenging? Absolutely. Impossible? No. It's an engineering problem, and engineering problems can be solved with sufficient technology and understanding. The initial energy calculation shock. When Alcubierre first published his warp drive paper in 1994, he included calculations for the energy requirements, and the number he arrived at was, to put it mildly, astronomical. He estimated you'd need energy equivalent to the total mass energy of Jupiter. The entire planet, Jupiter, converted completely into pure energy according to Einstein's famous equation relating energy to mass. Let's put that in perspective because the scale is almost incomprehensible. Jupiter has a mass of approximately 1.9 times 10 to the power of 27 kilograms. That's 1.9 followed by 27 zeros. Using Einstein's mass-energy equivalence, converting that mass completely to energy would yield roughly 10 to the power of 45 joules. That's a 1 followed by 45 zeros. How much energy is that? Well, the Sun outputs about 3.8 times 10 to the power of 26 joules per second. That's the total energy output of our star every single second. To accumulate energy equal to Jupiter's mass energy, the Sun would need to shine for about 800 million years. And that's just the energy requirement for creating one warp bubble capable of faster-than-light travel. All the energy humanity has generated throughout our entire history, from the first fires lit by our ancestors to every nuclear power plant running today, totals something like 10 to the power of 21 joules. We'd need to generate about 10 trillion times more energy than all of human civilization has ever produced just to power a single warp drive flight. The gap between what we can do and what we'd need to do was so vast that it seemed to make the warp drive a beautiful mathematical curiosity, but utterly impossible in practice. Many physicists looked at this energy requirement and concluded that while Alcubierre's solution was mathematically valid, it was physically meaningless. Sure, the equations allow for a warp bubble, but if creating one requires energy we couldn't possibly generate, even with technology centuries or millennia more advanced than ours, then what's the point? The warp drive remained theoretical in the most impractical sense of the word. But here's where the story takes a fascinating turn. Because Alcubierre's energy calculation was based on his initial geometry for the warp bubble, and that geometry, while mathematically sound, wasn't optimized. It was like building the first prototype of an airplane and discovering it needs an impossibly powerful engine. Then, assuming flight itself is impossible, maybe the problem isn't flight. Maybe the problem is that specific design. Some physicists started thinking about ways to modify the warp bubble geometry to reduce energy requirements. Could you reshape the bubble to make it more efficient? Could you change how sharply space-time curves at the boundaries? Could you adjust the size or configuration of the bubble to achieve the same effect with less energy input? These weren't idle questions. They were serious scientific inquiries that led to breakthrough after breakthrough, and within just a few years, researchers discovered that Alcubierre's original energy estimate wasn't a hard limit at all. It was just one possible design point, and with clever modifications to the geometry, they could reduce the energy requirements dramatically. Not by a little, by factors of thousands, millions, billions. The door that seemed firmly shut was opening wider, and what came next would transform the warp drive from a beautiful impossibility into something that future civilizations might actually be able to build. The question wasn't whether a warp drive could exist anymore. The question became, what technology would we need to develop to make it practical? And that's a question that has real answers, with real pathways forward, that we can discuss seriously instead of dismissing as pure fantasy. Progressive energy reduction breakthroughs. The first major breakthrough in reducing warp drive energy requirements came in 1999, just 5 years after Alcubierre's original paper. A physicist named Chris van den Broek published a refinement of the warp bubble geometry that changed everything. Van den Broek was thinking about the mathematical structure of the bubble itself, particularly the relationship between the interior volume and the exterior footprint. Alcubierre's original design featured a bubble that was, essentially, as large on the outside as it was on the inside. Simple, straightforward geometry. But Van den Broek realized you could do something more exotic. What if the interior of the bubble could be larger than it appears from the outside? This sounds like science fiction, but remember, we're already warping space-time. We're already violating everyday intuitions about geometry. Why not warp space in ways that create these kinds of dimensional paradoxes? Van den Broek's modified bubble design featured a narrow throat connecting the interior volume to the outside universe. From an external observer's perspective, the bubble might look relatively small, but from inside, the volume could be much larger, providing plenty of space for a spacecraft while minimizing the energy needed to warp the external space-time. It's like those old science fiction stories about spaceships that are bigger on the inside than the outside. Except this version actually works within general relativity. When Van den Broek calculated the energy requirements for his modified geometry, the results were stunning. The energy needed dropped from Jupiter's mass energy down to roughly the mass energy of the Sun. Now, the Sun has about 1,000 times less mass than Jupiter. So we're talking about a reduction by 3 orders of magnitude. Still an absurd amount of energy, absolutely. You'd need to convert the entire Sun into pure energy to power one warp trip, but it proved the principle. The energy requirements weren't fixed. Better geometry meant less energy. The problem was becoming an engineering optimization challenge rather than a fundamental impossibility. But the real game changer came in 2012. Harold White, a physicist working at NASA's Johnson Space Center in Houston, published calculations that reduced the energy requirements by an almost unbelievable factor. White was specifically interested in the sharpness of the warp bubble's boundaries. Alcubierre's original design featured relatively sharp transitions from normal space to warped space, like a cliff edge. You'd have normal space-time. Then suddenly, within a very short distance, you'd transition to extremely warped space-time. White proposed making these transitions much gentler. Instead of a cliff, imagine a gradual slope. The space-time curvature would change more slowly, extending over a larger region. This means the warping at any given point would be less extreme, even though the total effect, the net compression in front and expansion behind, would be the same. Think of it like the difference between a steep mountain trail and a gentle incline. Both get you to the same elevation change, but one is much easier to climb. When White recalculated the energy requirements using this smoother geometry, the numbers dropped dramatically. His paper suggested that with the right configuration, you might be able to create a warp bubble using energy equivalent to the mass of just 700 kilograms. 700 kilograms? From Jupiter's mass, roughly 2 times 10 to the power of 27 kilograms, down to 700 kilograms. That's a reduction by a factor of about 10 to the power of 24. 10 trillion times less energy. Let's be absolutely clear about what 700 kilograms of mass energy represents. Using Einstein's equation, that converts to roughly 6 times 10 to the power of 19 joules, that's still an enormous amount of energy. It's about equal to the total energy humanity generates globally in an entire year. It's roughly equivalent to the energy released by 15,000 megatons of TNT. It's in the range of the largest thermonuclear weapons ever designed, multiplied several times over. So we're not talking about something you could power with a car battery or even a nuclear reactor. But here's the crucial point. It's no longer absurd. It's no longer we could never possibly generate this much energy even if we wanted to. It's in the realm of with sufficiently advanced technology, this becomes conceivable. Fusion reactors, if we perfect them, could theoretically approach these energy outputs. Antimatter, if we could produce and store it in large quantities, would provide even more compact energy storage. Some far future technology we haven't even imagined yet might make 700 kilograms of mass energy seem almost trivial. White's work did something profoundly important. It moved the warp drive from the category of beautiful but useless mathematical curiosities into the category of extremely difficult but not fundamentally impossible engineering challenges. And that distinction matters enormously. Because impossible means we give up. Extremely difficult means we get to work. NASA's Advanced Propulsion Physics Laboratory, where White works, exists specifically to investigate these kinds of advanced concepts. They're not promising warp drives next year or even next century, but they're treating the warp drive as a serious scientific problem worth sustained research attention. They're asking, what experiments could we conduct today that might help us understand the physics better? What technologies would we need to develop first? What intermediate milestones could we aim for? This is the difference between science fiction and science. Science fiction says we have warp drive and it works because the plot needs it to work. Science says the equations suggest warp drive is possible. The energy requirements are still enormous, but potentially achievable with far future technology. And here are the specific research directions we should pursue to make progress. One is entertainment. The other is a roadmap, however distant the destination might be. And there's one more crucial piece to this puzzle. One more problem that needs solving before a warp drive could ever work. Because even with 700 kilograms of mass energy, we face a fundamental challenge. The warp drive doesn't just need energy, it needs a specific kind of energy that seems almost magical, negative energy. And understanding what negative energy is, why it's necessary, and whether we can actually generate it in useful quantities, that's where we're headed next. Because negative energy is real. We've detected it in laboratories, and it might just be the key that makes faster than light travel possible. Part 3. The energy problem solution and negative energy. Understanding negative energy. Now we need to talk about something that sounds like it shouldn't exist. Something that seems to violate common sense and basic physics intuition. But it's absolutely real. We've measured it in laboratories, and it might be the key to making warp drives possible. I'm talking about negative energy. When most people hear negative energy, they think of a deficit, an absence of something. Like negative balance in your bank account just means you have less than $0. But that's not what physicists mean by negative energy. We're talking about something far stranger. We're talking about energy that has opposite properties to normal energy. Energy that pushes instead of pulls. Energy that creates repulsive gravity instead of attractive gravity. Energy that curves space-time in the opposite direction. And here's what makes this crucial for warp drives. To create the space-time geometry that Alcubierre's equations describe, you need negative energy. Regular positive energy won't work. It curves space-time the wrong way. If you tried to create a warp bubble using only normal positive energy, you'd create the opposite effect from what you want. Space would expand in front of your ship, and contract behind it, pushing you backward instead of forward. Think about gravity for a moment. Mass creates a gravitational well. It curves space-time so that objects roll toward the mass. This is positive energy doing its thing. But to create a warp bubble, you need space-time to curve the opposite way in specific regions. You need something that creates a gravitational hill instead of a gravitational well. Something that pushes space-time outward instead of pulling it inward. That's what negative energy does. Now here's the part that sounds too good to be true but isn't. Negative energy actually exists. We're not speculating. We're not hoping. We've detected it. We've measured it. The effect is called the Casimir effect, discovered by Dutch physicist Hendrik Casimir in 1948. Here's how it works. Take two flat metal plates and bring them extremely close together. I mean really close, just a few nanometers apart. That's billionths of a meter. In the space between those plates, something weird happens. Quantum field theory predicts that even empty space, even a perfect vacuum, isn't truly empty. It's filled with quantum fluctuations, virtual particles constantly popping in and out of existence. These fluctuations carry energy. The vacuum itself has energy density. But between those two plates, something changes. The space is so narrow that only certain wavelengths of virtual particles can exist there. Longer wavelengths physically can't fit. So the energy density between the plates becomes lower than the energy density of normal vacuum outside the plates. And that difference creates an effective negative energy region. The result: the plates are pushed together by this effect. We can measure this force. It's tiny, incredibly tiny, but it's real and measurable. The Casimir effect proves that negative energy exists in our universe. It's not theoretical speculation, it's experimental fact. Several laboratories around the world have measured the Casimir effect with high precision. The force matches theoretical predictions beautifully, and those predictions come directly from quantum field theory, one of the most successful and well-tested theories in all of physics. So when physicists talk about negative energy, they're not engaging in wild speculation. They're discussing a real, measurable phenomenon that we understand mathematically and can produce in controlled conditions. Now here's where hope meets challenge. We know negative energy exists. We can create it, but the amount we can generate is absolutely minuscule. The Casimir effect between two plates produces negative energy equivalent to maybe picograms of mass. That's trillionths of a gram. And remember, Harold White's optimized warp drive design needs negative energy equivalent to several hundred kilograms of mass. We need to scale up our negative energy production by a factor of about 10 to the power of 17. That's 100 million billion times more negative energy than we can currently produce. To put that in perspective, if scaling up technology were like climbing floors in a building, we're on the ground floor and we need to reach a building 17 floors tall, where each floor is 10 times higher than the last. Is this impossible? Here's where things get interesting. There's no law of physics that says we can't generate large amounts of negative energy. The Casimir effect proves the principle works. What we lack is the technology to scale it up. We need better understanding of quantum field manipulation. We need new materials, possibly metamaterials with exotic properties. We need methods to shape and control quantum vacuum states over larger volumes. These are engineering challenges, not fundamental physics roadblocks. Difficult? Absolutely. The kind of difficult that might take centuries to solve? Probably, but impossible in principle. No. And that distinction is everything. The geometry challenge. Let's say we somehow crack the negative energy problem. We figure out how to generate hundreds of kilograms worth of negative energy and maintain it in a stable configuration. We're still not done, because creating a warp bubble isn't just about having enough negative energy. It's about arranging that energy in precisely the right geometric configuration to create the space-time curvature we need. The warp field has to have a very specific shape. Remember, we're trying to create a bubble where space contracts in front, expands behind, and remains flat in the middle. The field strength needs to be strongest at the boundaries of the bubble and weakest at the center. The transition from normal space to warped space needs to be smooth enough that we don't require absurd energy levels, but sharp enough that the bubble actually moves. Harold White's calculations suggest the optimal shape looks like an American football, elongated, with the strongest warping at the front and back, tapering to a relatively flat region in the middle where your spacecraft sits. But maintaining this shape isn't a one-time setup. It requires constant dynamic adjustment. As your warp bubble moves through space, you're constantly encountering variations in the space-time around you. A distant star here affects local space-time slightly. A gas cloud there creates minor gravitational effects. Even the cosmic microwave background radiation, the leftover energy from the Big Bang, creates subtle variations in the fabric of space. Your warp field needs to compensate for all these perturbations in real time. Think of it like surfing. A surfer doesn't just stand on their board in a static position. They're constantly shifting their weight, adjusting their stance, responding to how the wave beneath them changes from moment to moment. A warp drive would need to do the same thing, except instead of adjusting a surfboard, you're adjusting the curvature of space-time itself. And you need to do it thousands or millions of times per second with extraordinary precision. Is this impossible? Again, no. Our current spacecraft already perform complex real-time adjustments. The James Webb Space Telescope maintains the alignment of its mirror segments to within nanometers. GPS satellites adjust their clocks to account for relativistic time dilation. The International Space Station constantly adjusts its orbit to maintain altitude. These are all examples of precision control systems operating in challenging environments. A warp drive would need even more sophisticated controls, absolutely. You'd need sensors capable of detecting minute changes in space-time curvature. You'd need processors capable of calculating required corrections faster than those changes propagate. You'd need field generators capable of reshaping the warp bubble on microsecond timescales. But these are engineering challenges, not physical impossibilities. They're problems that sufficiently advanced technology could solve. Speed possibilities and practical implications. Here's where things get really exciting. If we could build a warp drive, how fast could it actually go? And the answer is going to surprise you. There's no theoretical maximum speed. Seriously, the Alcubierre metric doesn't impose any upper limit on how fast the warp bubble can move. Want to go 10 times the speed of light? Technically possible. 100 times. Also possible. 1,000 times. Still within the mathematical framework. The faster you want to go, the more energy you need to pump into maintaining the warp field. But it scales linearly, not exponentially. Double your speed, double your energy requirement, not double your speed, quadruple your energy requirement, like you'd see with conventional physics. Let's think about what this means practically. Light travels at about 186,000 miles per second. At that speed, light takes about 4.2 years to reach Proxima Centauri, our nearest stellar neighbor. With a warp drive moving at 10 times light speed, you'd make that journey in about 5 months. At 100 times light speed, just over 2 weeks. At 1,000 times light speed, you could cross the entire Milky Way galaxy, 100,000 light years from edge to edge, in about 100 years. The entire galaxy, traversable in a human lifetime. Every star system we've observed through telescopes becomes a potential destination. Every exoplanet we've discovered becomes somewhere we could actually visit. The universe transforms from an untouchable cosmic display into humanity's potential neighborhood. But before we get too excited, let's remember the challenges. We still need to solve the negative energy problem. We still need to develop the precision control systems. We still need power generation technology far beyond anything we have today. Even with Harold White's optimized design requiring just 700 kilograms of mass energy, we're talking about energy levels that dwarf current human capabilities. Conservative estimates suggest we might see the first experimental warp field, a tiny bubble maintained for a fraction of a second in a laboratory, within 200 to 300 years, a functional spacecraft capable of interstellar travel. Maybe 500 years from now, possibly longer, that assumes continuous technological progress, stable civilization, and sustained investment in advanced physics research. 500 years sounds like an impossibly long time, but consider this. 500 years ago, humans were just beginning to explore Earth's oceans. We didn't know other continents existed. We thought the world was far smaller than it actually is. Now we're talking about exploring not just our planet, not just our solar system, but potentially the entire galaxy. That's not science fiction anymore. That's a long-term engineering project with identifiable milestones and solvable challenges. The warp drive represents something profound. The possibility that the universe is actually accessible to us, not just through telescopes, but through direct exploration. It's the difference between looking at pictures of distant mountains and actually climbing them. And while the climb ahead is incredibly steep, at least we can now see the path forward. The math works. The physics allows it. The engineering is monumentally difficult, but not fundamentally impossible. And that changes everything about how we think about humanity's future among the stars. Part 4. Geometry, Speed, and Alternative Theories. While the Alcubierre warp drive represents our most promising pathway to faster-than-light travel, it's not the only theoretical framework physicists have explored. Remember those other 4 theories we mentioned at the beginning? Let's take a quick tour through them, because each offers fascinating possibilities and unique challenges that help us understand why the warp drive stands out. Wormholes represent one of the most elegant solutions to the distance problem. Instead of traveling faster than light, you'd create a shortcut through space-time itself. Imagine folding a piece of paper so to distant points touch, then punching a hole connecting them. That's essentially what a wormhole does. Travel through it, and you could cross from one side of the galaxy to the other almost instantly, regardless of how many light years separate those locations in normal space. The beauty of wormholes is that you're not actually exceeding light speed. You're just taking a shortcut that makes the journey shorter. But here's the catch. Natural wormholes, if they exist at all, would be microscopic and incredibly unstable. They'd collapse almost immediately. To hold one open long enough to travel through, you'd need massive amounts of negative energy. Same problem as the warp drive. And even if you could stabilize a wormhole, you'd first need to physically travel to wherever you want the other end to be, which defeats the purpose unless you're building a permanent transit network between established destinations. Quantum entanglement is absolutely real and has been proven countless times in laboratories. When 2 particles become entangled, measuring one instantly affects the other, no matter how far apart they are. Einstein called it spooky action at a distance. because he found it philosophically disturbing. But here's the frustrating part. You can't use entanglement to send information faster than light. At least not with our current understanding. Imagine you have two magical coins that always land on opposite sides. Flip one and it shows heads. The other instantly becomes tails. Even across the universe. Sounds useful, right? Except you can't control which side your coin lands on, so you can't transmit a message. The correlation is instantaneous, but information still can't travel faster than light through this mechanism. Some physicists are exploring quantum teleportation, where quantum states might be transferred across distances, but this remains highly speculative with enormous practical obstacles. Tachyons are hypothetical particles that always travel faster than light. While normal particles can never reach light speed, tachyons can never slow down to it. For them, light speed is the lower limit. Even stranger, as tachyons lose energy, they speed up. To slow one down would require adding energy. The problem? We've never detected a tachyon, not once. Some physicists argue they can't exist without creating causality problems, potentially allowing information to travel backward in time and generate logical paradoxes. String theory suggests they might exist under certain conditions, but they remain purely theoretical. Modified physics at extreme scales represents less a specific theory and more a category of possibilities. Some physicists think Einstein's relativity might not be the final word. At extremely high energies or in certain quantum conditions, the rules might change. Maybe light speed isn't actually absolute. Maybe at scales we haven't explored, space-time behaves differently. Some quantum gravity theories suggest that at energies approaching the Planck scale, space-time might become discrete rather than continuous, potentially modifying how light speed functions. But this is highly speculative, with zero experimental evidence. So why focus on the warp drive? Because it's the only one where scientists can calculate specific energy requirements, design spacecraft configurations, and identify technological milestones. The others are either pure speculation or face the same fundamental obstacles without the same detailed theoretical framework. When NASA investigates faster-than-light propulsion, they study warp drives. When physicists publish papers about building interstellar spacecraft, they're working on warp drive designs. It's not just the most promising theory, it's the only one that's genuinely engineerable, however distant that engineering might be. Part 5. Future, Timeline and Philosophical Implications. The Roadmap to Reality. So when could we actually build a warp drive? Let's be honest and realistic. Not soon. Probably not in our lifetimes. Likely not in our children's lifetimes either. But the fascinating thing is that we can identify specific technological milestones we'd need to achieve. This isn't vague speculation anymore. It's a roadmap, however distant the destination. Milestone 1. Generating significant negative energy. We need to go from picograms to kilograms. That's roughly 17 orders of magnitude, a scaling challenge unlike anything humanity has ever attempted. This probably represents our biggest hurdle. We need breakthroughs in quantum field manipulation, possibly metamaterials with exotic properties we haven't discovered yet, and methods to control quantum vacuum states over much larger volumes than laboratory-scale Casimir cavities. Conservative estimate: 100 to 200 years before we can generate even gram-scale negative energy. Another century beyond that to reach kilogram scales. Milestone 2. Precise space-time manipulation. Even with negative energy, we need technology capable of shaping it into the correct geometric configuration with extraordinary precision. We're talking about maintaining a dynamic warp field that adjusts thousands of times per second to compensate for variations in surrounding spacetime. This requires advances in sensor technology, control systems, and our fundamental understanding of how to manipulate spacetime curvature at will. Conservative estimate: 150 to 300 years. Milestone 3: Power generation and storage. Harold White's optimized design needs energy equivalent to 700 kilograms of mass. Even our most advanced concepts, fusion power or antimatter, fall short of these requirements. We need something beyond current physics, possibly involving zero-point energy extraction or technologies we haven't even conceived yet. Conservative estimate: 100 to 200 years for the underlying power technology. Longer to make it practical for spacecraft. Put it together, and we're looking at the first experimental warp field, a tiny bubble maintained for fractions of a second in a laboratory. Appearing maybe 200 to 300 years from now, a functional spacecraft capable of actual interstellar travel. Perhaps 500 years, possibly longer. 500 years sounds impossibly distant. But remember, 500 years ago, humans were just beginning to sail across Earth's oceans. We didn't know continents existed beyond our own. The world felt vast and mostly unexplored. Now we're contemplating sailing across the galaxy. That's not just technological progress. That's a complete transformation in what's possible for our species. The universe awaits. Here's what keeps scientists working on these problems, despite the enormous timescales involved. The fact that we can even have this conversation, that we can identify specific engineering challenges rather than fundamental impossibilities, means we live in a universe far more accessible than we once believed. For most of human history, the stars were forever out of reach. Not just practically unreachable, fundamentally unreachable. Even with near light-speed travel, the universe is so vast you could only visit a tiny fraction of it. But if warp drive becomes reality, everything changes. The galaxy becomes explorable. 100 to 400 billion stars, countless planets, potentially other forms of life. All become destinations we could actually visit. Think about the philosophical implications. If we develop warp technology, humanity transforms from a single planet species into an interstellar civilization. Every exoplanet discovered becomes more than a curiosity in telescope data. It becomes a place we might actually go. Every mysterious signal from deep space becomes an address we could investigate. The universe stops being something we passively observe and becomes something we actively explore. And maybe, just maybe, we'll discover we're not the first. Perhaps other civilizations have already solved these problems. Maybe they're out there right now, traveling between stars, using technologies we're only beginning to imagine. Maybe we've been looking for the wrong signals, searching for radio waves when we should be detecting gravitational signatures of warp bubbles moving through space. Or perhaps we are the first. Maybe humanity will be the species that figures this out. That becomes the first interstellar civilization in our region of the galaxy. Either possibility is profound. The mathematics says it's possible. The physics says it could work. The engineering challenges are enormous, but not insurmountable. We're at the very beginning of what might be humanity's longest and greatest journey. 500 years from now, someone might look back at this moment, when we first realized the stars weren't forever beyond reach, as the beginning of our greatest adventure. The universe is waiting, and getting there is just a matter of time.